Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hakim bin Azami, DE220124. Okay, today I'm going to make a video demonstration about BEJ20801 Electronic Engineering Laboratory 2. Okay, and my lab partner is Sundus Awil Khalif, AE200087, and we are from section 5. Alright, here this Lab 2 is about design PI and PID control system using Simulink. And if we continue for the PID block diagram, here it will we created it on the Simulink, as you can see over here. And then delay time, rise time, also peak time. Okay. And also maximum overshoot. So now we will continue to make as this 5.1.4 or figure 1.1 figure 1.14 show over here. As you can see, it's the same. And then we're going to set up our parameter, and for each P, PI and PID control. So first thing first, we're going to make for P controller, which is everything is 0. You need to set everything to 0. Here also 0, and this one 0.1. Okay, as you can see here, KP equals to 0.1, and if we run, we will make this graph like I send it in the lab sheet. So we open the scope. Need to wait a bit. Okay, here are the scope. As you can see, it's almost the same like on the P controller. Over here we can see the overshoot right here, or we can use the calculation over here, maximum overshoot. Also we can, from here we can take the delay time, rise time, peak time, and also setting time. So I already done the calculation, and I already submitted the result. As you can see here, 0.1 equals to the rise time is about 0.37 seconds, while the setting time is about 0.84 seconds. Here you can drag the cursor tool. As you can see, around 0.4. Okay, over here it starts the setting time. I take about 0.2% of the final value. Yeah, 6.889, and we calculated with 102%, we will get 0.84 seconds, and we will get 7.026. Okay, then we get the percentage overshoot. Make sure it become percentage because it wants it. Okay, this for proportional gain KP equals to 0.1. How about 0.3? So we just replace it with 0.3 and we run it again. If we run it again, we will get the second figure. I send it over here. Yeah, there it is, where the overshoot is 10%, 10.557, 55% off. So we make it 56 to make it more better because it's over 5. And then setting time, you can see 0.65. Go here. 0.65 is around here. Started to settling down. And then rise time is equal to 0.23 seconds. You can see the proportional gain KP is the parameter that affects the performance of the controller. Where it, if you can see from the KP 0.1, the where the peak becomes smaller, you can see. If you can see in the KP equals to 0.1, the peak is there, but we cannot see the proper peak. So we make the proportional gain much higher, which is 0.3. And as you can see in the figure 2, you can see the peak. So over here we can make the calculation based around the overshoot and the overshoot and rise time and also setting time. Okay, next one we can continue with PI controller. So PI controller where it will included with the integral gain, which is here we use proportional gain 0.2 while integral gain is 0.1. So we insert it here and we run, and you will get this graph over here. So we open the scope and there we go, it's the same. You can see the overshoot is 8.152%. What is the difference? You can see within both of these contour and this graph between figure 3 and figure 2. And next we continue with integral gain, which is 0.5. We make it more higher, 0.5, and then we run. We open the scope. There we go. We can see that the graph is much now we can see the graph are more stable than before with integral gain 0.5. Here we got the for 0.3, 0.25 seconds, and the setting time is 0.6 seconds, while the integral gain 0.5 we get 0.33 seconds and 1.57 seconds setting time. Okay, for the integral gain, what does it affect to our PI controller performance? Where you can see between the two figure, between figure 3 and figure 4, it makes it more stable than figure 3. If you can see the after the peak, it's peaked down more below than the setting time, while you can see in the figure 4 it's much more stable where it doesn't go beyond the setting time. Okay, here also the answer. Yes, it will become for our optimum performance for the graph. Okay, so we continue forward for the PID controller where we're going for derivative gain. So we reset back to integral gain 0.1 while our derivative gain 0.01 is much more smaller. So you can see here K, but you can drag it, I believe. Yeah, and you can see the inside, and we can run. After we run, we will see the hold on a second. Why is it over there? Oh, this one I wrong. Thank God that I look over here. Okay. Integral gain still the same, 0.5. Okay. Now it will be the same, where overshoot is 22%. Okay, that's correct. Okay, where you can see here the between figure 4 and figure 5. Figure 4 and figure 5. Okay, figure 5 with the derivative gain, you can see the graph become much more smoother, where it doesn't have a dip or anything, just after the peak we go on. But you can see that there's a steep over here. So we continue with our derivative gain, we add it into 0.03 and then we run it. You can see it will become much smoother. Yeah, over there it's like a flow over here where you go down very much smoother than before, than in the previous figure. Okay, So as you can see, the rise time is a bit higher, just a little bit. Setting time is also a bit higher, but the overshoot becomes much more smaller, around 4 to 5% now, like that. We don't want higher overshoot because it can cause to make our calculation much more unstable. So what does the derivative gain effect into the PID controller performance? Where as it's almost the same, where derivative gain equals to 0.03, much more stable and smoother than 0.01. And also it's leveling out the oscillation caused by the changes in the set point or disturbance, where it has better scopes in the graph than the figure 5. So KD also become a crucial role inside PID controller, where each P and PI and PID, which is proportional and proportional integral and proportional integral derivative. Okay, control. That's all for me, thank you. And for the next question, 7 and 8, it will concluded by Sundas Abdul Khalif. Thank you.
Faculty Electrical and Mechanical Engineering. Tonight I want to present lecture, especially questions and conclusion. So let's start. Advantages of P controller. Based on the given figure of the P control response with different values of Kp proportional gain, it can observe that with Kp01, figure 1 response has a small overshoot, but it takes longer time to reach step point compared to Kp 0.0.3, figure 2. Based on the experiment results shown in figure 1 and figure 2, there are several disadvantages of using P controller. First one, steady state error. In both figure 1 and figure 2, it can be observed that there is steady state error, which means that the system does not reach the desired set points. This is a common disadvantage of P controller, as they do not have an integral action to eliminate the steady state errors. Second one, overshoot. In figure 2, there is significant overshoot of the output response. This can be a problem in many control systems, whereas overshoots can lead to invisibility, instability, or even damage to the system. Third one, timing dependency. P controllers are required for timing to achieve optimal performance. In figure 1 and figure 2, it can be observed that changing the value of Kp has been significant impact of the system. The effect of the second experiment, the effect of the response when integral gain is increased. Increasing integral gain in PI controller while keeping the corresponding gain steady will increase the effect of the integral activity on the system reaction. Particularly, increasing the integral gain will increase the rate at which integral control gathers mistake over time, coming about in more noticeably. Attachment to the output of the framework. This can be seen as increasing the integral gain can cause the control activity to build up errors as well rapidly, leading to the rapid temperature reduction of that will cause the framework output to overshoot the required set point, increasing the integral in BI controller while keeping the proportional gain constant will increase the effect of the integral on the system response. Third experiment is when the relative gain is increased as well. The relative chain KDI is one of the 3 parameters used in PDI proportional integrated relative controller. is proportional integrated derivatives with control is control loop mechanism employing feedback that is widely used in industrial control system and variety of the other applications requiring continuously modulated. Figure 5, the KDI value is 0.01 if the KVI value is less effective of response is less. In figure 6, the value is 0.03 in figure 6 when compared to the figure 5. The KDL value is more precise. It presents the rate of the change of the errors and uses anticipated future errors and reduce passes. A high KVL will result in faster response to remove the errors if set up to higher. It can cause the system become unstable and oscillated. If the KVL value is more, the effective of response is more. Moreover, in figure 5, the KL value is less effective by the response. This is lower, whereas in figure 6, the KVL value, the KD value is more effective if the response is faster. Finally, conclusion. The B controller is a simple and well used controller, but it has several disadvantages, including overshoot, limited ability to eliminate steady state errors, and needed to careful tuning to adapt the changes if process dynamics. Increasing the integral gain in BDI controller while keeping the proportional gain concept can improve the system response and reduce the steady state errors, but it must be done in conjunction with appropriate proportional gain adjustments to maintain and avoid overshoots. The rate of change KDI is another parameter used in BDI controller, which represents the rate of change of the errors and is used to anticipate future errors and reduce passes. However, a high KVL value system may cause the system become unstable and oscillate. The KDL value in figure 5 is 0.01, and increase in figure 6 leads to faster effect of the response. Finally, the selection of the control strategy ultimately depends on the specific requirements and characteristics of the system being controlled. That's all. Thank you, Doctor.